Okay, so for part 2 of the Unit 2-3 notes here, we'll pick up with example 4. And so again, this one's hopefully a pretty standard review question for most of us, but a good chance to go through and review some of those major concepts, right? So this one they're giving us, it's a ball that's thrown from the top of a building at a 20-degree angle, and they give us the velocity, right? So just drawing this, representing this here, I'm throwing the ball off at a 20-degree angle at 20 meters per second. So the first thing I'm going to go ahead and do is I'm going to go ahead and just find my horizontal and my vertical components, right? Because I know that I always want to break those up into components. And so I get about 18.8 meters per second for my horizontal component, and I get about, when I do 20 times sine of 20, I get about 6.84 meters per second for my vertical. So part A here asks, how long does it take the stone to reach the ground below? So the stone goes up and then it falls back down, right? Not quite in that squiggly of a pattern, but whatever. Okay, so the building is 45 meters high. And this was a question where we traditionally would break it up at the top. I used to always tell you guys, right, use the fact that the final velocity is 0, and then find the time that it takes to go up, and then find the time that it takes to go all the way down. We actually don't have to do that though, right? So instead, if I actually just use, so I'm going to be using my vertical measurements, and I'm going to go ahead and reference this equation where my final height equals my initial height plus v0t plus 1/2 at squared. Okay, so all I'm doing is I'm looking at my vertical measurements for my position as a function of time relationship here. So let's just identify all of our information, right? Well, the final height would be when it hits the ground, which I'll define as 0. The initial height would be the positive 45 meters above the ground that it started at. The initial vertical velocity was, again, that 6.84, and then I have the time, which I don't know. That's what I'm looking for. And then my acceleration, because I've defined upward as positive, my acceleration would be negative. So it would be negative 1/2, 9.8. Obviously, you could include the negative over here. I went ahead and just pulled it out front. The only downside of doing it this way, because again, there's absolutely nothing wrong with doing this. The only downside is it's a quadratic, right? So you get two possible answers. So if you solve this quadratic formula, if you solve this quadratic function, you get two possible answers. You get either negative 2.41 seconds, which obviously doesn't make a whole lot of sense, and we'll look at why, or you get positive 3.81 seconds, okay, which is actually then my answer. So the negative 2.41 seconds is representing what would happen if this ball actually went backwards in time, assuming that it had continued that path, right? So that negative 2.41 seconds is just saying if this ball were thrown up from ground level before it reached that height, instead of being thrown from the top of a building, it would take 2.41 seconds to reach that height, and then 3.81 seconds from that point on. But again, that doesn't really have any physical meaning for us because we know that the rock has started from the top of the building here, so that doesn't really mean anything. Okay. The 3.81 seconds, again, hopefully had you broken this up at the top of the path and then found the time that it takes to go all the way down, you should have gotten the same 3.81 seconds regardless of which method you chose. So again, hopefully this wasn't too bad. To find the speed of the stone before it strikes the ground, this is one to watch out for the common mistake, right? The most common mistake that a lot of students tend to make here is they find the vertical velocity when it hits the ground and then feel like they found the answer because they did all of that calculation. But the thing we have to still consider is as the rock hits the ground, it still has that constant horizontal motion as well, right? So I know the horizontal component is 18.8 meters per second at any instant in time. So I do need to find the vertical component, right? So using my measurements, again, let's just think through what we know. Well, I know my initial vertical velocity is 6.84. I know my acceleration due to gravity is negative 9.80 meters per second squared, since I've defined positive 6.84 as going up. And I know my time. I found the time to be 3.81 seconds before it goes from here to the ground. So once again, I do not have to break it up at the top. Now, if you do, there's nothing wrong with that. You're just making yourself up a little bit more work than you have to, right? So if I'm looking for the final vertical velocity, I'm just going to use my velocity as a function of time, right? I'm going to use this one because I know 3 of those 4 measurements. So I'm just going to I'm going to plug in, right, my initial velocity of 6.84, my acceleration of negative 9.80, and the time that I just found, no matter what I got from part A, that's the time that I'm sticking with, right? So I'm going to plug in those measurements, and now I find my final velocity to be about negative 30.5 meters per second. Okay, so when I calculate that, I get about negative 30.5. Keep in mind the negative simply tells me it's going down, which makes sense, right? This object is falling down once it hits the ground. So then if I'm looking for my final speed, again, be careful. This is not my answer. This is the vertical component of my answer. Okay, so it's moving downward at 30.5 meters per second, whereas the rock is also still moving over at 18.8 meters per second. So if I want to find the actual speed, I need to find the resultant, I need to find the hypotenuse of those two measurements. So a simple Pythagorean theorem, right, 18.8 squared plus 30.5 squared, and I find the speed, the magnitude of my velocity, is 35.8 meters per second. Now the nice thing about this question is they didn't ask me for the velocity, so I do not have to worry about the angle, but keep in mind if they did ask me for the velocity, I'd also want to find maybe this angle with respect to the perpendicular line, the vertical line here, or this angle. So then example 5 here, this one is a fairly complex one because this one will require us to set up a system of equations. Okay, so this is one that, I mean, technically we still know how to do it, there's nothing new, but the fact that it involves a system of equations makes it a little bit more challenging. And obviously the first part of this question is just making sure you're comfortable with the context here. So it says a ski jumper leaves traveling horizontally, right? So here's the ski jump, and it is just a level jump. And the jumper goes off, the jumper is just a dot here, but she goes off at 25.0 meters per second. Then it tells us that the incline of the slope is 35 degrees. So what that's trying to tell me then is this angle right here is 35 degrees, or if you prefer to think, the angle of decline would also be 35 degrees. Okay, so they're asking, as she jumps off, she doesn't stick with the ground, she jumps off of it. So as she jumps off, she goes through the air a little bit, and then where does she land down here? Pretty good parabola there for me, pretty good curve there for me, but we're looking for what the distance that she actually goes is. So in other words, we're actually looking for this measurement right here. Okay, so it's kind of tough to see that in there, but we're looking for how far did she go from here to here. So I'm going to call that distance, I'm just going to call that d to represent the total distance that she's traveled down the slope. So where does she land? Well, in order to set this up, probably the easiest way to approach it is we're still going to break this into components. And what I mean by that is I'm still going to form a right triangle just out of that distance instead of out of the velocities. So if I break this up, the reason I want to do that, again, I know this angle here is 35, so that tells me then that the delta x that she travels would be d times cosine of 35. Similarly, the delta y that she travels would be d times sine of 35. So the benefit of doing this, the whole point of doing this, right, is that I'm able to represent both my horizontal and my vertical components in terms of the same distance. It allows me again to represent them in terms of the same distance. And so that, obviously, if I'm setting up a system of equations, will help me reduce some of the variables that I have. So anyway, let's go through and let's identify all the information we know. Well, for the horizontal measurements, it's easy enough, right? The only equation I'm ever working with is v equals delta x over t, and let's think about what information we know. Well, I know her horizontal velocity because she left the ramp going 25.0 meters per second, and that was entirely horizontal. I do not know the specific distance she went, but I'm going to call that distance d cosine 35. I'm going to represent that distance in terms of the d down the ramp that it went. And then finally, I don't know the time, right? I don't know how long she's in the air because I don't know how high it is, and therefore don't have the time. So if I was setting up the horizontal components, I get stuck, right? I've got the two variables there, so I get stuck. But then if I look at my vertical components and do the same type of thing, my initial vertical velocity is 0 because she's leaving horizontally. My acceleration I know is 9.8 or negative 9.8. Let's just maybe make this negative 9.80, and we'll look at why. I'm actually going to define my two positions separately, and what I mean by that is I'm going to say my initial position. So I'm going to say my initial position up here is, let's just say that's a positive d sine theta, so d sine 35. And then my final position would be down at this location, which I'll define as 0. So again, this is 0 because this was d sine 35 above that. So I'm going to define that as 0. And then the other variable, again, I don't know it, but the other variable that I can work with is time. So then when I set up the relationship between my final position, the initial position, right, I'm just using my position as a function of time equation, right? My initial velocity was 0, which actually simplifies this a lot. I don't have to worry about a quadratic, at least not right now. I don't. My final position was 0. My initial was again d sine of 35. And then I'm going to make this a negative 4.9 since I defined my acceleration as negative 9.8 t squared. So then solving for that, I get, if I go ahead and solve somewhat, I get d sine 35 equals 4.9 t squared. But obviously at this point I still have two variables. But all it boils down to now is a system of equations where if you look closely, you have the same two variables, right? D and t are in both of my equations. Okay, so truly nothing too crazy here. And there's not necessarily a right or a wrong way to solve this. What I would probably recommend is I'm going to go ahead and solve the top equation up here for t. So I'm going to multiply both sides by t and then divide by 25. So I get t equals d cosine of 35 divided by 25, right? And then I'm going to take that whole mess and I'm going to substitute that whole mess in up here. So what that ends up giving me then is d sine of 35 equals 4.9, and then I'm squaring this whole quantity, so I'm going to go ahead and distribute that squared to each of them. So this would be d squared, this would be cosine squared of 35, or cosine of 35 squared, that whole thing, right? And then 25 squared on bottom. So it looks like a little bit of a mess, but keep in mind all of these are just numbers with the exception of d. I can in fact cancel one of my distances out, right? That takes away the fact that the distance could be 0, but we already know that if she started at 0. Okay, so if I factored that out, I actually could have an answer of d equals 0. But I know that at 0 distance she started in the same location. So I'm looking for the other one. So then from here it truly is just a matter of rearranging this equation and solving for d. So I would multiply both sides by 25 squared. So I get 25 squared sine of 35. And then all over once I divide by 4.9, and keep in mind this is again cosine of 35, that whole thing, squared on bottom. Okay, so at this point it's just the algebra. I will leave that calculation to you to make sure you guys can double check it. But anyway, hopefully it's not too bad. Okay, so I lied. I said I'd leave that to you, but I will go ahead and give you the right answer in case you want to check it. So it should have been about 109 meters down the ramp, down the slope. Okay, so again, hopefully you got that one. And I think I will go ahead and stop this part of the video here, and then we'll pick up the last couple of examples in part 3.